Okay, this video is one that I promised my students in MAE 3013 this summer, and I'm going to work a few problems out of the tail end of chapter 13 of our textbook. And to do that, I'm going to need to be able to write, so I've got my writing paper set up. Let's turn on my pen. I should be good to go. Okay, and I'm going to work problem 13.4, and it should be problem number 12. And the question is, given a u is equal to x squared plus y squared, is this function harmonic? And then can I find the harmonic conjugate for this function if it is in fact a harmonic? The test to see if it's harmonic says we need to take two second partial derivatives of this function of u, and we need the second partial of u with respect to x. And so to do that in two steps, the partial of u with respect to x, we're going to call ux is equal to 2x, and uxx, taking one more partial derivative, is equal to 2. And the partial of u with respect to y, we're going to call uy is equal to 2y, y, and then uyy is equal to 2, and then the partial uxx plus uyy, both second partials, does not add to 0, and so this thing is not harmonic because we want uxx plus uyy equal to 0. That's false in this case, so this problem is not harmonic, and we continue on. And so the next one we will look at is problem number 16, that says u is equal to the sine of x times the hyperbolic cosine of x. So first question is it harmonic? And we need a partial of u with respect to x. That means we're going to ignore, oops, I did this wrong. Let's see if I can erase that piece. There we go. One other piece, maybe. There we go. That needs to be a y. Okay. So we're going to ignore the y term while we're taking the partial with respect to x. So ux is simply equal to the cosine of x, and uxx is equal to the minus the sine of x. Oops, I lied. Cosine of x times the cosh of y. We hold these terms, the second term, constant while we calculate the first term. There's our uxx. Uy is equal to the sine of x times the hyperbolic sine, and uyy is equal to the sine of x held constant times the cosh, cosh of y. And we can see if we're going to add these two terms together, they do in fact sum to 0. So it is harmonic. And now we can take the next step and find the harmonic conjugate by recognizing that ux must equal vy, and that uy must equal minus vx to satisfy the Cauchy-Riemann requirement. And what we're going to do is, given that we know dv dy right here, at least something close to it, let's integrate with respect to y and find v. So the integral of vy is the same as the integral of ux is the same as the integral of the cosine of x times the cosh of y. Remember, we're integrating with respect to y. Okay, so dy, and that gives us that v is equal to, we're integrating with respect to y, so v is equal to the cosine of x times the hyperbolic sine of y plus some unknown h of x. Pardon me while I answer a phone call, and I don't know how to pause this video, so that's just the way it goes. Hello? Okay, send it back, please. Thank you. Okay, so continuing on, we have v up to an unknown h of x right here, but we also know the derivative of v with respect to x right here. Hi, I'm got someone in my office, so hang on a second. I have got to finish this video that I'm making. It's probably going to be another 20 minutes, maybe. Why don't you call me again and check with me again in 20 minutes. All right, so sorry for the interruption, but that's life. Continuing this video, so I know that I have v right here, and I have minus dv dx is this thing. So let's take v and take the derivative with respect to x and compare to this term right here. So grab my pen back, and so v subscript x means dv dx is equal to the derivative of the cosine is the minus sine of x times the hyperbolic sine, oops, let's erase that, times sin h of y plus h prime of x. This term right here, its derivative. And I do see that when I take the negative of this, I get a minus sine x, hyperbolic sine y, which matches perfectly. And there is no sign of a term here to deal with, so h prime of x is equal to 0. Therefore, h of x is simply a real constant. And so I have confirmed that v of x and y from right here is this equation plus a constant for that h of x. And so v is equal to cosine of x, hyperbolic sine of y plus a constant. And that is our answer. Now going to problem 13.4, problem number 18. A similar kind of question, different equation. We have u is equal to x cubed minus 3x y squared. First question is it harmonic? And so ux is equal to 3x squared minus 3y squared. And then uxx is equal to 6x. Uy is equal to minus 6xy, and uyy is equal to minus 6x. And I can see that these two terms do in fact sum to 0, and so our u function is harmonic. Now let's find its harmonic conjugate, realizing that this is also vy, And this is also v, oops, lost my pen, is also vx with a minus sign in front of it, minus vx. So we're going to take our vy, which is ux, which is that term, and we're going to say that v is equal to the integral of vy dy is equal to the integral of ux dy is equal to the integral of 3x squared minus 3y squared dy, or v is equal to 3x squared y minus 3y cubed over 3, so it'd be minus y cubed, plus some h of x only, not a function of y. So there is v, but remember we have dv dx right here, and so using this v that we just wrote out, which would be this v, we'll take its derivative with respect to x. And so vx is equal to, oops, that moved on me, I didn't want that. Let's get that back out of the way. So vx is equal to 6xy from this term over here to the right. That's all. That's our only term with respect to x. And over here, minus vx is minus 6xy. So vx must equal to 6xy. That is a match. We do add in, oh, let's see, plus h prime of x, which leads us to conclude there's a match perfectly here and here, giving h prime equals 0. And if h prime is equal to 0, then h of x must equal a real constant. And that's all. And so the v function is equal to 3x squared y minus y cubed plus a constant. And that would be then the answer to this question. And I will leave here and stop the video.